But let's get started on the reason we're here. I'm excited to present our speaker today, Dr. Laura Fackrell. Um, she is currently a postdoc at Northern Arizona University, a position that she actually started recently. She recently graduated from the University of Georgia, which is just a drive away. And when I originally emailed her, I actually thought she was still there, but this is actually really great to be able, again, to hear that she started her postdoc at Northern Arizona University. She also got her master's at UGA, and then her bachelor's degree was in geology at the University of Kansas, which she got in 2012. We were talking about this briefly, but I think her research is unique in that she takes a different approach than a lot of people when thinking about astrobiology and surface processes on Mars, which she's going to be talking about today. She really thinks about the critical zone. And I actually, learned about Laura through one of her talks at a conference recently, where she was presenting on some of her work with soils and doing analog work with soils. And I'm really excited that she's here, and I will let Dr. Fackrell take it away. Thank you so much again for chatting with us.
Yeah, no problem. Good morning, everyone. Thanks for the introduction, and thanks for the invitation to kind of speak with everybody today. So yes, I just recently graduated from the University of Georgia, where I finished up some of my work there. We're looking, and today that's what I'm going to be speaking a lot, is kind of some of the results in the research that we focused on for those applications. And then now I'm actually working on a different kind of project at the Northern Arizona University. So I've moved from Mars back to Antarctica, and so I'm working on that kind of thing. So my focus in science tends to be on, in some ways, in critical zone science, on the exploration of lots of different things, but it's mostly focused on the interactions that microbiology and geology have together in different environments, especially extreme environments, and like how those interactions work together and what that can tell us about the rules. And I like extreme environments because in extreme environments, you kind of learn where we don't understand the rules yet, where it looks like the rules are being broken, but actually it's just that it's the things that we don't understand yet. And so that helps us to really kind of open new avenues and understand how all these processes work in a bigger perspective. But today I want to focus on this concept of applications of critical zone science in the exploration of Mars. And I'm going to focus, there's a lot of ways that this can apply to Mars, and I'll kind of mention a few of them, but I'm going to focus most of that on some of the work I did for my dissertation, where we worked on agricultural aspects. So how does this affect the potential to do agriculture on Mars, and like what does that mean, and how do we make it sustainable? And so that's kind of more of the focus of the talk, and some of the early results that we did from some experiments using regolith and growing plants and trying to understand how we mimic conditions on Mars, and like how do plants and things respond to that, and what does that mean for an overall bigger picture. Go ahead and get the slides advancing. Let's see if that, there we go. Perfect. And so first I'd like to acknowledge some of my fellow authors and committee. So Paul Schroeder and Christian Klinzak and some other of the authors that have helped to publish some of this work, as well as the committee and other people who have collaborated and supported and helped to assist with like field work in different aspects, and various funding sources from Clay Mineral Society and Sigma Xi, and the National Science Foundation's support for critical zone observatory work, and all those things that kind of help to support and be able to accomplish all these different things. And just a little outline for how we're going to approach this talk and move forward through the topic. First, I'm just going to give a little bit of context about critical zone science and about exactly what that is and what kind of how that relates to Mars more specifically. And then we'll focus in on how that relates to specifically in situ resource utilization for agriculture on Mars. And so what would that look like, and how do we approach that from like a critical zone perspective, both in using regolith as a resource, but also in different approaches and some of the results that we've seen of how plants respond to some of those conditions. And then that'll kind of help us to look at some of the conclusions and where we want to move forward with this. So the critical zone, as pictured here, is basically defined as to extend from the lower atmosphere, about the top of the vegetation on Earth, down into bedrock where meteoric water has influence. So it's basically like that package of that area of Earth, and in that area, there's a lot of interactions of different kinds of processes of geologic and biologic and chemical and all these things that are interacting together to produce this living zone of that's dynamic and that has all these different implications and complex relationships. That if you kind of just zoom in on one relationship, you're missing a lot of the picture. And so critical zone science tries to like bring that back to looking at a whole system perspective to kind of understand how these processes work together. And they seek to couple the tools of multiple disciplines to better understand these processes from that system-wide perspective, so that we can understand not just the chemistry, but everything that's happening, and trying to piece together that puzzle and see what that big picture is. And it's often applied to various ecological and other things on Earth. And one of the common applications is what are the anthropogenic implications? Like what are anthropogenic activities? What effect do they have on these processes? Especially things like agriculture are a pretty common focus. And so last year, as part of the decadal survey, we put forth a white paper that kind of extended this definition to Mars. And that a few people have kind of looked at that before. We kind of wanted to extend, like, how would we approach this and what does that mean? And what would that do? Like, what does that look like on Mars? And how does that affect how we research Mars? And so that definition basically took a similar definition to the critical zone on Earth, where we have the Mars critical zone would extend from that lower atmosphere, that portion that more directly interacts with the surface, and it would extend down into impact fractured bedrock, where you have like different ices and different things, and perhaps even groundwater that could circulate when conditions permit or may have permitted in the past, depending on heat flux and all sorts of different things that would allow for that to happen. And it's like kind of that zone. And in that zone, you have all these different interactions happening, geologic, chemical, perhaps, we don't know the answer to this one yet, but perhaps biological, in the past or in the present. And how does that work together to create the surface that we see today, and how that's changed over time? And what does that mean for potential habitability and how we understand how these processes work on Earth, or even just prebiotic chemistry, and what does that mean? So how do we approach this from the system-wide perspective to really kind of pick apart that understanding? And there's a lot of ways that this can be applied to Mars, whether it be from trying to understand how nutrient cycling, if it cycled or if it just transferred, or however nutrients move around on the Mars in the past or at present, how different geochemical reactions occurred and produced the current surface that we have. One of my favorite ways to look at is how you then apply terrestrial analogs to Mars. That's more of what in line of some aspect of what I do now with working in Antarctica. Though we're not Mars focused, we are working in a Mars analog. And so how do we understand how the processes that happen in those analogs, what do they reveal about Mars? But then what do those processes differ? What would they reveal that isn't applied to Mars? And so recognizing the both the comparisons, but also the things that we can't compare because they're not similar, and really trying to understand that from a system-wide perspective, so we can approach that from that angle. And then what we're going to talk about today is how we apply this to more of the anthropogenic effect side. So that's a big aspect of critical zone work, is what is the anthropogenic effect on these processes? What does that mean? And is it sustainable? And so what can we do with that when we think about agriculture on Mars, where the resources are much more limited and there's a lot higher risk of just the nature of the exploration and the missions that would come from that? And so that's kind of where this comes in. And to kind of help with that, it's useful to provide a context of what exactly has happened in the past, several years of growing plants in space in general. And so just to give like a kind of a really brief history, and if you want a fuller history, then the paper that's referred here is actually a really good resource to kind of get started on that. There's a lot of information about what the history of agriculture in space in general. But this is a picture of one of the first systems used to grow plants in space that was developed by the Soviet space program. And systems like this kind of were just the initial, can we even grow plants at all? And what does it take to produce a chamber or an environment that actually allows plants to grow? And that was kind of like that first level of, we're just going to make it happen kind of systems. And those quickly developed into more of a focus on systems that were able to be more advanced and were able to actually like support not only just making the plants grow succeed, but also understanding a lot about plant physiology and our understanding of how plants respond, how they've evolved in the environment that they've grown up in for millions of years, and why gravity, like how gravity affects that and how they respond to microgravity. We've learned a lot about plant physiology from these kinds of experiments. And then more recently, after they've installed what was called veggie, and now that's been superseded by the advanced plant habitat, and both of those were installed aboard the ISS. But these are specifically designed, and these are the first that was the actual intent, where they were intentionally designed for food production. And so they've kind of graduated from not only learning about plant physiology, but can we expand this and expand our understanding and that foundation to kind of build on that foundation of actually doing this for food production in a way that you could sustain someone, and how you do that with limited size, space, and resources. And an important aspect of that is the medium you use to grow the plants in. Now that you don't have gravity to help water drain, or even in partial gravity where water will drain very differently through a soil than perhaps it does on Earth, or through any kind of medium, how do you set up a system that works with that? And so a really important part of how the systems work is that medium that's provided for roots, whether it's for a rooting medium to support rooting structures, or just a general growth medium that helps provide that structure for the plant, and can also be a part of the avenue that provides nutrients. As we set this up on Mars, this is just kind of an artist rendition of what that might look like from Soil 2016, and just kind of examining that. You have all sorts of things, and I like this figure because it kind of shows how regolith might be part of that picture. But when we're aboard the spacecraft, you're basically going to be using hydroponic option. That's the option that you have, that, or you're able to then install that, and that's a really good way, and they've kind of been able to develop that pretty well. But as you get to a planetary surface or a lunar surface, you have now additional mediums that are accessible. You have additional options, additional resources that you can use to kind of expand and diversify your approach. And so that, even though that, and so that's kind of like how we want to think about it, is like, now that we have a greater access to this greater diversity of options, how can we leverage those to create further fail-safes, to create a system that's diverse, both in that it creates multiple avenues of food production, so that in case one avenue of food production breaks down, you still have other ones you can rely on. And so that's just a food security issue, and how you can make it sustainable as far as for the crew, but also sustainable with resources, because now you're not putting all the strain on one avenue of resources, but you're spreading that out so you can have that more sustainable and actually likely more successful ability to support that aspect of a mission to Mars, the crewed mission to Mars. And so that idea of how you might apply regolith has been looked at a little bit in a lot of different studies. We have some initial work. Some of the more well-known studies come from like Wamelink et al., where they've taken some of the different Mars regoliths and analogs that they have on Earth, and they've tested them to see if plants will grow. And they found some cool results that were kind of that had potential that, yeah, it can technically grow. Just to kind of very briefly summarize what they found. But a lot of these early studies rely on some simulants, specifically some of the early simulants that were developed from the JSC Mars simulant and the Mars Mojave simulants. And these are both simulants that are developed pretty early on in our exploration of Mars. The JSC simulant was one of the first developed, and it was mined from like a palagonetic tephra deposit from the Pu'uinene Hawaiian volcano. And it was chosen because it has a similar spectral profile to certain dusty areas of Mars. And so it's a spectral simulant that has this very comparable spectral profile. The MMS simulant was developed a little bit later, but still pretty early on, and it's basically mined from a basalt flow. So they basically took a basalt flow that was from the Mojave Desert, and they ground it up and made a simulant out of it. And that was a geotechnical simulant. There was a few problems that the JSC wasn't really helpful for certain applications, and so they developed this simulant to kind of fill in that gap. And both simulants have been really important for providing a lot of foundational work in trying to understand and to prepare for any kind of thing you think of that you would need a simulant to test, whether it be rover testing or preparing for certain things. They've been really valuable for that purpose. However, they do lack a lot of characteristics that are important for things that you would want to know about for agriculture. So characteristics that plants would care about and that are going to affect plant response. And so they have a limitation to how far they can be used to really understand the feasibility of using regolith as a growth medium for plants. And so that's something that a lot of studies kind of rely on these two simulants, but there's only so much we can answer if we don't mimic these additional characteristics. Because of that limitation, both in general, but specifically in this case, they were looking at water extraction studies, because of some of the limitations of those simulants. Another group, kind of similar, at a similar time that I was doing my work, so we're both kind of going down this same avenue at the same time. but they developed a stimulant called Mars Global Stimulant, which instead of just taking one resource and grinding it up and like making, and this is kind of similar to Mars, they actually took multiple individual components, and they also, and the understanding that we have from data that we've been able to gather over the last few decades, especially data from, and it specifically chose Rocknest to kind of mimic, as we have like a really good mineralogy, an understanding of what the mineralogy and the chemistry and all the different, it's one of the most well-studied samples from Mars, just because of how Curiosity and everything has looked at that. And so they chose Rocknest as kind of like their base. And they actually put together a more specific recipe that more closely mimicked it, and tried to actually compared it directly to see like how well we're actually representing all of these different characteristics. And so that's a much more improved stimulant that they've been able to develop. And they've done it, and there has been a group that have done some agriculture work with it. More recently, they did this last year, and they found that it was rather limited in what it was able to do. And part of that was because this particular stimulant had a really high pH, which can be really limiting for plant growth. What's interesting though is that the pH that they measured was about 9.4, and that the only direct pH measurements we have for Mars, at least that I'm aware of, are from Phoenix Lander, and its range was about 6.7 to 7.9. And so that's actually a very different pH range. It doesn't mean that 9.4 isn't a relevant pH. If we only have pH from that one location, that we can't really say for sure that there aren't other pH ranges for Mars soil. And there are certainly other pH ranges for certain other materials on Mars surface, although maybe not for the soil, but there's definitely a range of pHs that we could expect on Mars depending on what kind of material you're looking at and where you are. And so 9.4 is not necessarily an irrelevant sample, but it does only show one end of the spectrum. And so that's kind of like, that's where we had kind of gotten to, is like, we're kind of still at this beginning point of just trying to see if it even is feasible and if it'll work, kind of like when we were first starting to grow plants in space. And so that's kind of, we wanted to take that and see what we can use from looking at this from like this critical zone perspective. What can we do with this to kind of approach the project? And so that's kind of how I came into what do we want to do for this project and how do I want to examine this. And so this is just kind of like a conceptual diagram to help illustrate the idea of how we approach the situation. And if you have a plant on Earth that you're trying to grow, and what are the resources that Earth provides that are able to like produce this productive thing, whether it be air or water and sunlight, whether it be in this soil that makes this natural growth medium that has all these different aspects to it, and the microbial community that occurs within that medium, how do you replicate that and how do you provide some of that same things for on a different planet? And so a lot of that is just about engineering and can be provided artificially through an artificial atmosphere or these closed environments or filtering water, providing light. But what is the best way to approach this particular aspect here, where we use microbes and a medium of some type, and that medium sourced from the regolith so that you don't have to bring it with you? How do we approach that? And so that's kind of what we wanted to explore here. So if we zoom in on the medium itself and on what, at least if you're looking at soil as a medium, what does that provide? And it's average soil on Earth, you usually have about 45% of minerals, about 20 to 30% air or water, depending on how recently it's rained or how the porosity of your particular soil. About 5% of that's going to be organics, of which you have some microbes. And so the total soil microbes, the weight of the soil microbes only make a really small fraction of that weight, but they're integral in how they change the soil and how they're basically a huge factor in how nutrients and how all of these things actually are cycled through the soil and what makes them mobile and available. And so they're a huge factor in the soil, and they have a huge, a very intimate connection to plants that has evolved over millions of years. And so like this organic and micro portion is a really key part of the soil that makes it able to support plant growth. And it's not the only aspect, but it's an important aspect. And if we look at Mars, it's an aspect that's probably missing. And so all these kind of balances that we see in an arable earth soil are suddenly gone, or changed, or a completely different balance. And we're pretty much left with, for the most part, something, and we don't necessarily know the answer for the microbes or other forms of life yet, or if there ever was, but we're kind of basically left with mineral and air. And how do we, and so we want to think about how do we then bring the rest of this back, especially I think these two factors here, the organics and the microbes, what do we do to bring those back? And how do we accurately represent this mineral-air relationship to actually mimic Mars so we can accurately see how plants would respond to it? And so that was kind of what we did. So the first step was really just looking at the mineral and air and how do we accurately represent that. And so we developed, because of the limitations we have of different simulants, and kind of at the same time as this other simulant that more recently came out, we were developing different simulants that were specifically geared towards agriculture and towards how do we mimic characteristics that plants care about. And so we developed 5 different ones that kind of cover a span of different materials that you could expect to find on Mars, and specifically materials that are potentially useful or very useful for different aspects of agriculture. And we created different recipes based on data that we have from different Mars rovers, especially Curiosity, and then also orbiting data, and trying to put together something that would be representative of what you could find on the surface. Whether it be that you have a phyllosilicate from which you can make soil aggregate pellets that would be for like a hydroponic application, or whether you want to extract acids or alkaline solutions so you can alter pHs, are some of the applications you could think about. But we wanted to see more of like what potential each of these profiles might have for a direct growth medium, especially the global soil and some of these other phyllosilicate simulants. But we included like this whole spectrum just to see like what is that spectrum, because not all, just to kind of understand like how plants respond to different profiles that you could potentially create from the materials available on Mars surface. So we put together recipes. We found materials similar to how the other simulant would have been pretty, where we kind of collected materials from the field. So you can see a familiar image here of the field site that we collected some of our phyllosilicates from, specifically our nontronite, and then some other some copiapite from an acid mine drainage site, which is similar to jarosite in a way. It's both hydrated and hydroxylated, and so it's kind of like in that family of compounds of iron sulfates, and as well as various basalts, both weathered and unweathered, to kind of produce some of these primary mineral bases. And we took that, and that's just a few in here. So like this is like our list of materials and where they came from. And we took that list, and this is just kind of like an overview of how that worked together to create an analog. But you take your material, crush it up, and you quality assess it to make sure the material is appropriate. And once you kind of have, you have a material that reflects Mars and that would be useful, you crush that up, you combine it together according to the recipes that we had designed. All the ingredients except for the soluble salts. We found the salts tended to be more evenly distributed and more placed in a way that was more realistic when we actually added them in solution. And so we would take the soluble salts, put them in solution in the proper concentration, mix them with the dry ingredients to kind of make a paste, and then you dry that overnight, and you end up having this analog that results that it's not just a dry mix. So a dry mix is useful in the fact that you have the right minerals there, but when you kind of go through this process, you would create an additional texture to the analog that gives it a more soil-like texture. To the extent that we can mimic soil-like textures, it kind of helps mimic that a little bit more. And so we create those analogs, and then we compared them to what we actually understand about Mars to really see if they actually match, and to see that at least these particular characteristics are matching what a plant would actually see. And so we did X-ray diffraction, we did reflectance spectroscopy, we did XRF, we did Moss-Bauer, and we compared it to what we have available from different types of data available from the surface of Mars. And we use kind of a scoring method to see how much that relates as far as like how closely it mimics. And so this is a method that's been used in other analogs as well. We followed the procedure that was given by Metzger et al., which was used for some analogs that were made for asteroids. And you basically just take your target and your simulant and you compare them, the values for whatever characteristic you're examining. And you take the lower of the two values. This is kind of like just a simple way of doing it. You take the lower of the two values and you carry that over into a third column, and then you add that up to create a score. And that score will be kind of bounded between 0 and 1. And the closer it is to 1, the greater amount of overlap that there is. And the further from 1, the less overlap. And we kind of established that if you have a score that's like 0.8 to 1, that's a pretty good score. You have a large amount of overlap, and so whatever characteristic you're comparing, you're probably overlapping enough to pretty accurately mimic that characteristic, at least in some aspects. And if you have kind of between 0.6 and 0.8. It's a little bit more moderate. You have a good amount of overlap, but you also have a lot of non-overlap. And so there's probably something that's important to recognize that are different. And so that's something important to know. Doesn't mean that you can't use a simulant for that comparison, just that you have to be aware of some of the things that are different about it, especially if it affects a really important aspect. And if it's below 0.6, you're not really overlapping enough to have a good comparison. And so we kind of compared some of our simulants. So we compared our global soil simulant is the one I'm going to present. And we kind of compared it both chemically to that. And you can kind of, and this, I think it's easier to see in this visual comparison, but this provides the actual numbers. But it's easier to see kind of in the graph. And this is just a plot of the chemistry of the different, and so you have Mars average soil, which just from the literature, what Mars average soil has been defined to be in the literature, as well as what we know, the results we have from rock nests specifically, as well as Govabeb, which is a second soil sample that was taken by Curiosity a little bit later, but is also in Gale Crater. And just comparing like that range of what we see there. And that it's right within range of all the different chemistry there. And so that's a really good sign that chemically, at least, it's a good match. But just as important, if not more important than as the actual amount of something there, is the format it's in. The mineralogy is really important to consider as well. And that also follows pretty closely, although our particular sample had less amorphous material than we predicted, and a lot of that comes from natural variation in the crystallinity of the materials that we use, which will also occur on the surface of Mars as well. There's a natural variation in some of those things. But overall, it provides a very similar mineral profile, so you're being exposed to the same minerals that you would expect from that global soil that the plant then has. That's what it's going to be interacting with. And if you add any microbes, any microorganisms to it, that's what they're going to be reacting with too. All right, so that's kind of how we develop these materials, and then we're able to, at least for materials that we have enough data. So for things like a carbonate, we're just starting to get a little bit more data that will be able to do similar comparisons and make and update those to kind of match. The more information we find, the more accurate we can become with these comparisons. Just to gives us that accurate mineral and air composition for at least a part of that, creating a part of that medium. And like I said, there's a lot of ways you could approach using regolith as part of providing growth mediums or rooting mediums or different aspects of agriculture, but we wanted to be specifically more as a direct medium. So how it would respond to these mediums directly. And so this is kind of some of the early results of that plant response to that specifically. And we did a lot of different experiments with microbial inoculation and nutrient availability and like salinity and different things. I'm going to just talk about one of the experiments that we did, but I'll kind of give you some context for the others as well. And so for this particular experiment, it took place in our growth room, which is where most of our experiments did, which kind of it's an insulated room that allows us to at least it doesn't allow us to directly control temperature or humidity, but it allows us to keep them in a particular range by just kind of controlling the system. And in this experiment, we used a plant called mothbean, and I'll talk about that in a second. And we used a combination of 3 inoculants that, again, I'll mention that in a second as well, but these are the 3 inoculants that we used to kind of look at this aspect of both putting we have mineral air and then adding this microbial feature back in. And then we used 4 of the stimulants. Sadly, the global soil stimulant, and I'll talk about this a little bit, that's actually the stimulant that's shown to have the most potential as a growth medium, that it's had pretty normal growth for some of the earlier experiments that we had done, but we had a limited supply of it, and so we weren't able to use it for this particular experiment. And I think the results are still useful to kind of understand like where we're at and like where we move forward. But we did kind of put that together, and we created a comparative stimulant that was like a control stimulant that was basically like used the same process and provided a similar textural environment, but was basically a blank, or was basically quartz sand and diatomaceous earth to kind of just create this mostly silica environment that would be very different from Mars chemistry. So that it was not really so much a strict control as much as it was a comparative control to see what that would respond with. And we amended them with coconut coir, and we tried it with both fertilized and unfertilized. And let me talk about 3 of these aspects with a little bit more detail. So mothbean, if you're not familiar with it, is a plant from kind of semi-arid regions of India and Pakistan. It's nutrient content, so it's a bean that has a very similar nutrient content to soybean. Lots of protein, very nutritious, with a lot of potential to be like a really good resource for protein and for other nutrients. But it's more drought resistant than soybean. And so it's a extremely drought resistant legume, and it has also a moderately salt tolerance. So it's a little bit more hardy. And so there's a lot of potential, and it's really kind of a hot plant in certain areas of agriculture that are looking at resources for semi-arid regions and arid regions where things are harder to grow. And so it's a kind of a cool little plant in that way. But we experimented with a lot of different plants early on, and this one just kind of provided the most useful range of results. And so that's what we use in a lot of our later experiments, to kind of just provide that starting point. And then based on that plant, so you kind of choose the plant and then you choose the microbes, because that relationship tends to be very host specific sometimes. And so you can't really choose your microbes until you know which plant you're growing, because that will determine a lot of that. And so these are different species of organisms that we've used with mothbean before, and that we found really helped it, and that we exposed it to several conditions on specifically salinity, I think, was the most productive one, where we exposed it to Mars-like salts and different things, and it was able to really improve the plant's response in kind of these more stressful conditions. So we know that it was a microbe that could help improve the response to at least some aspect of Mars. And that it had some usefulness there, and it could be applied in a way that was really easy to amend the soil with it, and so it's like an easier application that would be feasible to do on the surface. And so that's kind of the logic behind choosing these particular groups, and that combined they made was the most beneficial that we saw was when they were combined. And then amending the soil with coconut course, that's the other part, and that is kind of to reflect that putting the organic material back in the soil. And this is just kind of the starting point. We tried lots of different amendments, and any kind of amendment that basically helped to lighten the soil was helpful. And so and without the soil, it tended to be very heavy. So this is from a lot earlier work that we did. If you didn't have any kind of amendment, the soil tended to be very heavy, difficult for plants to penetrate, difficult to grow. But if you used only this organic material by itself, it tended to be more difficult to control the water and the moisture, and so it tended to also not be very good by itself. But if you combine them together, you actually had a pretty productive medium. And this is specifically with the global soil stimulant. The plants, they were harvested pretty early. It's about 15 days into their growth, so they weren't very old yet, but they had already achieved really good growth for the stage that they were at. But this is some of the early work. So this is early experiments. We didn't have microbes involved at this point yet, and it was just kind of like generally seeing what amendments and how they did. And so that kind of showed a lot of potential for that. And that coconut core kind of took the place of it's basically a form of inedible plant material. And so on Mars, you're going to have a lot of that. It's not going to be coconuts, but it will be other forms of plant material. And so that's kind of a starting point to kind of start exploring that side of it as well. So now we have that full picture where we're going to have water available from these different resources that we've been able to extract and process and filter. So that's being provided from that engineering perspective we talked about before. But we've also restored some of that organic matter by amending the soil with some of these things, and we've added the microbes back in. And then we have an accurate representation of the mineral profile as well. And so then we can kind of put that together to create this medium that allows us to achieve this goal. And we analyzed the data with these kind of methods of, because there was occurrence of things like how many growth stages were they able to achieve, what stress severity they experienced, above and below ground biomass, plant tissue analysis to see what nutrients were actually absorbed by the plants and like what that measured as, and then also saturated media extract, which allows you to see what nutrients are extractable from the actual growth medium. And so that's kind of just like a brief overview of some of the data we analyzed. And if you have more questions about the specific analysis, we can certainly talk about that. But I want to focus more on the results and like what we actually saw, because I think that's kind of the cool part that I think will serve best to our discussion, at least right now. And just as a brief kind of context of how stress severity was scored, we did a visual stress context, so what is visible in that stress. So if you're a crew member and you're looking at these samples, what visible distress are you able to detect? And like, can you detect that by just looking at it? And so just kind of like scoring that stress score from either from like a 1 being normal to the highest score, like a 5 or 4, depending on which scale we're looking at. That's extreme stress. And we analyzed it. In this particular experiment, the data was a lot more patchy, where a lot of things died or a lot of things didn't die. And so we had to stick to kind of this non-parametric analysis for things that we had enough data to analyze statistically, and otherwise just kind of like just this visual comparison. But I think it's a cool result that we see. And so that's just kind of a list of the specific tests that we did. Again, and we can go into that, and if you have questions about that more specifically, we can talk about those. But I want to kind of look at what we saw. And so how do plants actually respond to all of this? And we found that they germinated pretty well. Once you amend the soil, moth bean tended to germinate pretty readily, but they didn't get very far sometimes. And so with these particular 4 stimulants, they didn't really provide a very good growth medium overall. There was there was growth in some of the phyllosilicate ones, but it wasn't very healthy. And the inclusion of the inoculant didn't seem to make any statistically significant difference, except in one of the mediums, and that was actually our control medium. The plants grew pretty normally in that particular medium and had a significantly less stress. And so because they were fertilized in some of the experiments, but the fertilizer was only provided in a much lower amount. So, and actually the effect was stronger in the fertilized one, where they just had when you want to use a microbe, especially with legumes and rhizobium, you want to use a dilute fertilizer, because otherwise a plant won't associate with it, because it doesn't need the microbe to provide the nitrogen. And so if you provide too much nitrogen, it's just not going to establish that relationship. But if you provide a dilute fertilizer, it can actually produce the more productive variation, where you have the best of both worlds. And so we actually did see a significant difference between those plants which had the inoculants, either fertilized or unfertilized, but especially it was actually even stronger in fertilized, where there was a significant, and this heat map basically shows the difference between the effect size. And so whether or not the inoculant was significant and what that effect size was. And it was for that control where you had at least a viable medium, the inoculant helped. And so I think that was a really cool result, that even though we have these stimulants that weren't very productive for the most part, we could still see an effect of where these microbial organisms are helping. And if we had been able to include the global soil assembly, I think we would have seen some additional things that would have been really cool. But sadly, because we didn't have enough of it, and it was in the middle of a pandemic, so we couldn't get more of it at the time, that's one that is kind of left unanswered for now. But that kind of leads us to, what does this mean about, and what we move forward from this? And so again, I think one thing that would be really interesting is to go back and actually use this global soil stimulant to see how it would behave with this, because early results of that one had shown a lot of really productive growth, and I'd really like to see how the microbes are able to interact with that particular one. Also, development of more advanced organic materials. So instead of using coconut coir, which is not something you'd expect, it is a type of inedible plant material, but not one that you'd expect to have on Mars. So using this in cooperation with development of actual soil-like substrates, that is a pretty big area of focus of how do we use things like rice straw or wheat straw that are actually going to be expected large amounts of the inedible material that needs to be recycled. And so how do you help that process? As well as applications to other microbes and other plants, because there's a lot of variation in how plants respond to a lot of different things. And so you can't just stick to one thing. No matter how useful that particular plant is, you have to expand to other plants that are applicable and would actually be potentially grown there. And also and for me, the most interesting part is actually the nitrogen part of the story. And so a lot of the work I've done in the past has been with nitrogen cycle and how microbes are involved in that cycle. And it's a largely biologically driven process on Earth. And so how does that affect a closed system that you're going to build? And if you add rhizobium with legumes to the system, what does that affect? And can that replace or at least alter the cycle of recovering nitrogen to a source that's less prone to pathogenic infection, or what implications that have? And so that's an area that I want to move forward in and exploring that specifically, both for the moon and Mars, and then how does that deal with those materials? And so I think some of the conclusions is that extraterrestrial agriculture is going to be an essential aspect of exploration of Mars and beyond. And that critical zone science can provide that useful framework to approach that work and to kind of develop sustainable practices. And from that kind of approach, we were able to develop 5 different simulants that are useful for various aspects of agriculture. For our particular work, we focused on more as a direct medium, but there's a lot of other applications of that could be experimented with. And that relatively simple methods, at least for the global soil simulant itself, it was relatively simple methods that were able to make it viable. However, there is still a lot of questions that we haven't answered yet with it. We haven't yet tested it with perchlorates, and we did a little bit, but not. We didn't expand it. And there's lots of ways that you potentially treat perchlorates, and that's another conversation. And perhaps we can have some follow-up questions. But that's another aspect that needs to be explored further. And in general, regolith-based agriculture for like space exploration is a field that's kind of like still in its infancy in a large extent, and that we kind of need to step up to this next level of work to kind of bring it back to get it actually to a level that it's actually viable to be like for a mission. And so that's kind of like that next phase that we're trying to push towards, is getting this ready to be like that next step, and to get past the point of just doesn't work at all to the point of like, can we actually viably produce food production? And how does this, what role does this play as part of this multi and diverse agricultural approach? So, and that's kind of what I wanted to share. So if you have any questions, I think we have, hopefully I didn't take up too much time, but we have a little bit of time for some questions.